Hi, so can we move on from last time to a new technique? Now, this technique I'm about to cover now is probably the hardest one to get your mind around and to understand, but it's logical. So I hope you can keep up with my logic and understand it. I really want you to understand it. So, where does it apply? It applies when we've got a mixture of liquids. And we're talking about miscible liquids. If we had immiscible liquids, we'd use a separating funnel. But if you've got liquids that mix together, the most famous example of this is alcohol and water. If you've got an alcohol-water mixture, how do you separate it? Now, what we're going to use here is we're going to use the differences in melting and boiling points. Actually, no, we're not going to use melting points at all. We're going to use boiling points. Now, the boiling point of alcohol or ethanol, as the drinking alcohol that's present, there are lots of alcohols, but the drinking alcohol is called ethanol. The boiling point of ethanol is 78 degrees. And the boiling point of pure water is 100 degrees. So say you had them both, alcohol and water, mixed up, and you wanted to separate them. You might think, simple, just boil off the alcohol. You're right, boil off the alcohol. Because the alcohol boils first. Its boiling temperature is lower, 78. The alcohol boils, put it through simple distillation, put it through the apparatus. The alcohol will boil, go down that condenser. As it goes down the condenser will cool it back into drops of alcohol. Unfortunately, if you were to do it there, as the alcohol boils up, it carries with it droplets of water. Droplets of water go up as the physical bubbling happens, as the boiling happens, the droplets of water get carried up with the alcohol. And so you have coming out the end there, you have more pure alcohol, but you've still got some contaminated water. And so simple distillation won't cut it. Simple distillation is not good enough. We need an amendment. We need to change this apparatus, and we need to change it here. We need to change the apparatus so that we get purer alcohol and not just alcohol with water contaminating it. So we use not a normal simple distillation would give poor separation, as when the alcohol boils it carries with it some water, and so we get water contamination in the collected alcohol. Instead, we have to use a technique called fractional distillation, and fractional distillation must involve a fractional distillating column. And a short way of saying that is a fractionating column. But fractionating column, fractional distillating column, same thing. So let's have a look at this, and let's have a look at what the apparatus is and how it works. So, pretty similar to the previous apparatus, the difference is this fractionating column. So imagine this, there's still the thermometer, there's the alcohol and water mixture. We're going to boil the mixture using a Bunsen burner. As we boil it, the alcohol, being lower boiling point, will vaporize, and the vapors of the alcohol, ethanol, will at 78 degrees start leaving the mixture. As it does so, unfortunately, drops of water will go up with the alcohol vapors, and both alcohol vapor, that's alcohol gas, and water droplets will start going up this column. Now, this is the clever bit. As the 78 degrees alcohol vapors go up, then this fractionating column takes a bit of time, but the fractionating column will reach a temperature of 78 degrees. As the temperature is 78 degrees alcohol wants to be alcohol wants to be a gas at 78 degrees, whereas water wants to be a liquid at 78 degrees. Water is a gas above 100. So at 78, the alcohol will stay as gas. The alcohol gas will go up and up and up and up and up. The water droplets will form on the inside of the fractionating column, and the water droplets will drop back down into the round bottom flask that we started from. So the fractionating column gives a chance for the water that's being carried up, for it to form drops and drip back down into the flask that we started with. All the while, the alcohol vapors will keep going up. And you know that at the very top, if it's mainly alcohol, because the thermometer will register 78 degrees. And then that vapor will come from the T-junction down here, and it's being cooled here by air. But when it gets here, cold water cools it down. And the cold water here, water in, water out, the cooling effect of the cold water will make your alcohol gas turn back into alcohol drops, and the alcohol drops will come out the end there, and that will be fairly pure alcohol. Now, even with a fractionating column, there will still be some droplets that get carried all the way up and over and down. And what I say is, look, if you got 50-50 alcohol and water mixture with a normal column that's like half a meter that we do in school, we get about 99% pure alcohol, 1% water. If you want better than that, then you made the column, this column has to be longer, and you can make it 10 meters, and that would give you much better separation. But even then, you know, you get 99.9% alcohol. So I want to paint a picture to you that this is good separation. It's not perfect. There will be some contamination of the alcohol that you get as a function of the water droplets that are carried up and over with the alcohol gases going over. That unfortunately is unavoidable. And you could talk about different techniques, but this is the one that they use, and we can get whatever purity we want. It's just we can't get 100%. We can get, most places want, like, the bottles of alcohol labelled in schools, 95% they are. They're labelled ethanol. They are, in fact, methylated spirits. They're 95% ethanol and 5% impurities. And that, for most people, is way good enough to do whatever you want to do with it. So it's not an issue. Oh, my TV going off. I don't know why. Let me just get that back. I think it was my computer going off. Okay, so my computer went off, my TV went off. I'm sorry. Let's just carry on to the explanation. Now, I want you to learn this explanation. So when at GCSE they ask this, very few people get full marks. There's always people that miss some important aspect to this explanation. So learn it, please, and learn it. Actually, rather than learn it, I far prefer you to understand it. You can learn it when you got exams, parrot fashion, but I want you to understand it now. That'll make the learning much easier later. So, heat up the mixture. Temperature gets to 78. The alcohol starts to boil. turns into gas. It goes up the apparatus. Unfortunately, as it boils, it carries drops of water with it. The column gives time for these drops of water to drip back down and allows the 78-degree alcohol gas to continue going upwards. Further up the column we go, the purer is the alcohol, until at the top of the column we have about 99% alcohol contaminated with 1% water. This makes its way down the condenser, where the alcohol is cooled, condensed back into the alcohol liquid to be collected as fairly pure alcohol. Okay, so that is fractional distillation. I'll demonstrate it in the practical video, which I'll do next. But let's move on to the last technique. The last technique we need to know about is chromatography. Now, chromatography. I was trying to think of an analogy that might work, that you could think about. And the closest I got to was perhaps consider a river moving downstream, rivers flowing, and you throw in there some twigs and some apples. Well, the twigs are very light. They'll get carried by the current further down, and the apples, not being as light, being a bit more dense, will be carried down by the water, but not as quickly. And that kind of idea is what chromatography uses. So chromatography always has two phases. There's something moving, like the water in a river. And there's something not moving. That's like the river bed that's not moving, over which the water has to kind of work its way past and through to get downstream. Now, rather than using those kind of like crappy words, let's get to proper words. The proper words are: chromatography involves a stationary phase and chromatography involves a mobile phase. Now, most of the time, you guys have done chromatography using little pieces of filter paper. So filter paper is the stationary phase, and you've put drops of water on that filter paper, or you've stood the filter paper up in a beaker where the water has risen up, and that rising water, that moving across water, is the mobile phase. So the mobile phase moves across the stationary phase, and then, cleverly, if we put any chemical, the mobile phase carries the chemical. Say it's a mixture, that carries the mixture, and within the mixture, the different components all travel at different speeds. That's the crucial thing. The different components will travel at different speeds with the mobile phase across the stationary phase. So when we've got a mixture, and we often use a mixture like felt tip pens. Felt tip pens are a number of different coloured chemicals to make up a particular colour. So a particular colour may have 2 or 3 different chemicals to make up that colour. And we put that on filter paper, and as the water travels across it, these 3 chemicals will get carried with the water along in the direction of the travel of the water, and one of the chemicals will travel faster, one of the chemicals will travel slower, and the other one will be intermediate, and the 3 will end up separating out. The further the water travels, the better the separation that we see. Now, I was standing in the way of that so that you'd have to listen to me. But let's run through the points that I've got on my slide, because when I just witter on, I miss the odd point. So let's see. Chromatography as a technique is a very useful technique. Yes, undoubtedly very useful. It's used very widely in chemistry laboratories all over the world. Very useful technique for separating chemicals from each other as chemicals travel at different speeds across, for example, a filter paper. And I would say across a stationary phase. Chromatography involves some chemical travelling over or through a stationary medium, a stationary phase. So travelling with a mobile phase through a stationary medium. So it's like water travelling over filter paper. Water is moving, the filter paper is not. Every chromatography involves that type of situation. And then you spot chemicals on there, and then the chemicals go with the mobile phase. The chemicals go with the mobile phase, and I've lost my image again. Why is that? Sorry, my computer TV seemed to decide to turn off. So in school, the stationary phase is usually filter paper, the mobile phase is water, and that water travels across the filter paper. As the water moves, if you put the mixture on it, it will carry the mixture along with itself, and within that mixture, the individual chemicals, they will travel at different speeds. As time goes on, the chemicals will therefore separate. Although the technique will separate a wide variety of chemicals, in order to see the separation, which is what we want you young minds to actually see it happening, then we can't use colourless chemicals because you won't see them with the water. We use felt tip inks, etc., from felt tip marker pens, and when we use that, then we do see the different chemicals that are within the inks. They show up as blobs of different colour at various places across that filter paper that you're using. Chromatography in the real world always involves a mobile phase and a stationary phase, but doesn't always involve a filter paper and water. For example, GLC, very important technique in chemistry laboratories for separating chemicals and determining, for example, things like how much alcohol is in your blood. If you've done for drunken driving, down the police station, they will have one of these machines. That passes a gas as the mobile phase. It passes it through a non-reactive powder, aluminium oxide, which is inside the machine. So the blood is put in, the gas carries it through the different speeds. All the different chemicals travel at different speeds. They know the speed of alcohol. So they know when alcohol reaches the end, there's a detector that detects it and says, oh yeah, this alcohol's coming out. And they will know from the quantity that comes out whether you've got a lot of alcohol or a little bit of alcohol in your bloodstream, if they're taking you down the police station to do a test, etc. Anyway, real life applications of chromatography are huge. There are loads of them. Let's teach you something else though. That is what you do is called simple chromatography. You remember doing it like this? This is a filter paper. This is water. The water will, by capillary action, it will move up the filter paper. As it goes up, the ink spot, which is a mixture of chemicals, will move with the water, but the individual chemicals within that ink spot will travel at different speeds, so that as time goes on, the ink spot will separate into blobs of different colour. Now this ink spot has got lots of different chemicals in it. Some of the inks we use on felt tip pens only have one, and therefore they only get one blob. Some have two, some have three. I think some of the darker colours, they have like four, and then you get four blobs. But can you see the blobs are separating? So if we get a pair of scissors and cut up that yellow, cut the yellow out, we've separated the yellow chemical from the red chemical and cut that out with a pair of scissors, and so on. You can separate them by cutting them out. It's just that those chemicals will be on the filter paper. And then you can dissolve them to get the chemical off the filter paper, etc. There is another better way of identifying the chemicals that you have, and that's with measuring the RF values. Now, about chromatography, I'll come back to RF values in a minute. No chemical can travel faster than the solvent, like the water. So you can't get the chemicals traveling faster than that because it's the solvent that's carrying the chemicals with it. Longer we leave the chromatography experiment to run, the bigger will be the distances between the various blobs and the better the separation. Chromatography needs to be stopped before the solvent gets to the top. If the solvent gets to the top and you leave it running, the other chemicals will catch up and everything will end up at the top. And that's no good. Right? You've gone to all this trouble to separate them, and if you don't keep an eye on it and leave it, everything ends up at the top, and you've got your blob of ink at the top rather than the individual chemicals that make up that ink as separate blobs before that. So keep an eye on it. And it's the RF value. The RF value doesn't change. Whether you're running it for 5 minutes or 10 minutes, the RF value will still be the same. So let's have a look at what the RF value is, because it's used to identify the chemicals that you might have, because data books will tell you RF values for various chemicals, and you can see. Okay, so this is how we work out RF values. Say the blob was there and the water travelled all the way to there. You'd measure that distance. That's this distance that the solvent has travelled. Measure that distance and then measure the centre of your blobs. How much has that red blob moved? Well, it may have moved 0.8 of that distance. The distance the red has travelled, the distance the red's travelled over the distance the water's travelled, the RF value would then be 0.8. If it was blue and it only went up half that distance, then the RF would be half of the value, 0.4. Now if you run it for half the time and that water was down here, then these two blobs would be down here. All of the distances would have gone down by half and the RF value would still be the same. So RF values are quoted in data books. And if you've got a certain blob with an RF value, you can try and work out from the RF value what it is. It's a bit like boiling temperatures. If you know something boils at 100 degrees, then you might think, oh, it's water. If you know the RF value is a certain exact value, then you know, oh yeah, it might be this, it might be that. So, really important, RF values. I'm not sure if RF values are in at GCSE, certainly in at A-level, but GCSE, they might ask you to calculate one because it's so simple, but I'm not sure if they're quoted as in the syllabus as being required. I want you to know about them. I think they are in the syllabus. I might be mistaken. I might be mixing it up with my A-level. And that's it. So we'll stop there, and that next time, all these separation techniques, practical demonstration of them. See you then.